All right, here we go. Round three of me attempting to record this lesson, baby. Here we go. Come on, bring me some luck here today. Today is the 18th. And just FYI, this should have been the second unit, but I oopsied and hopped ahead to the third unit because we used to always do equations first, and then we did um, lines and slopes and all that as unit two. And then so we switched it and that happened. And I just it doesn't matter. At the end of the day, you're going to get what you get. But so like this technically on the curriculum is unit two, but we're doing it as our third unit. And also, so you know, we're going to go back and do a district assessment on lines and slopes, just not until after break. I don't want to worry about it. So anyways, this is our unit three, but it's technically the district's unit two. And it's all about functions. Have you guys ever heard that before? Functions. Okay. So what we're going to spend our time today doing is we want to learn how to identify. So we are identifying functions. Some math lessons you just charge in and you feel like this is so concrete. It's like step A, step B, step C. This one is not like that. You need to give me about 10 minutes and just come along for the ride. Stay alert, ask questions, stay awake. And then here in about 10 minutes, you'll understand what a relation is. You'll understand how to determine if a relation is a function. But it's very awkward and weird. So just like I said, hang out, come along for the ride, write stuff down, and ask lots of questions. But that's that. So by the time you leave here today, you're going to be able to look at a relation and say, yes, you're a function because this, or no, you're not a function because of this. That's the goal. So before we can talk about what a function is, this is the part that I think is honestly the most confusing, which is weird. We have to define this word. And I'm not really huge on definitions, but I think that you need to know this word so that when I say it or someone else says it, you know what it means. A relation. There's no way you know this answer, but I'm going to throw it out because what the heck? Do you guys know what a relation is? I mean, I don't know why anyone would know this. In mathematics, a relation is a set of points. And you know your points commonly by the name X, Y. We sometimes call them ordered pairs. Like if you had numbers in place of X and Y, if it was like the point 3, 4, then that's an ordered pair that says to go right 3 and up 4. So if you have a set of those points or ordered pairs together, they form as a group collectively as a gang of points. We call them, hey, look, it's a relation. That's what we call that. Okay. So for the first relation or for the first point in our relation, make sure you copy these down exactly because these ones I actually planned out. And other than my terrible drawing at the end, I was successful once with these. So I'm going to do them again. So that is an ordered pair, right? The X is -2 and the Y is 3. And I'm going to have 3 more ordered pairs that I want you to put into your relation. The next one is 3, -1. And then we have 0, 4. And then we have 5, -1. So if you already understand what I'm talking about, then great. But if you don't, let me say again, those 4 points collectively, if you saw them walking down the street, you'd say, hey, look, it's a relation, right? It's a gang of points. It's a group of points. It's a set of points called a relation. So the first part of this lesson for today is to give you an idea as to what 3 ways might I see a relation. And one of them is already on the board. So the first thing you're going to see sometimes for a relation is this one. It's just a set of ordered pairs. No graph, no arrows, no diagrams. It's just a listing of all the X's and Y's in the relation. Okay. And by the way, a relation can be a relation. If you take a look up here, don't do this in your notes, but if I did that, that is still a relation. A relation doesn't have to have 3 or 4 or 50 points. 1 point makes up a relation. It's a very small relation, but it is still. Okay, so we're going to carry on with this normal relation. So the second thing you're going to see is called a mapping diagram. And this is where we really hit at what is going on with points, like what is going on with X's and Y's. And the idea with a mapping diagram is we want to show someone visually how each X becomes his corresponding Y. There's so much math going on behind the scenes that we never get to see. But I'm going to show you an example right here. So like there's a machine somewhere. It's an invisible machine. You can't see it, but out there it's there. And what it's saying is if you feed me, the machine, a -2, I will give you back out a 3. That is called a mapping. When you input something and it gives you something back out, something else, we call that a mapping. And there is a mapping for every one of these points in the relation. You could also feed the machine a 3 and it would go beep, boop, 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 and it would spit you out a -1. That's a mapping, and so on and so forth. 0 is mapped to 4. 5 is mapped to -1. So every time you see an ordered pair, an X and a Y, the X is the input that you fed into the machine, and the Y is the output that you got out of the machine. Clear? Clearish, clearer than mud, I hope. So here's what a mapping diagram will accomplish. And I'll show you, this will take a second. We kind of have to set this up. But what I want you to do is I want you to make an X with like a long, tall box underneath it, like this. And then I also want you to make a Y with a long, tall box underneath it as well. So I want to continue for the next couple of weeks to talk about this idea of inputs and outputs. It's what's going to get us through the functions unit, is you understanding that every point that exists is a result of someone giving an input and a machine giving an output. Okay. So having said that, what we're going to do is we're going to put all of our inputs into the box on the left, and I like to put them in order from smallest to biggest. So when you look at the inputs from the mappings, the smallest input, you would agree, is -2, right? Now, inputs, remember, are your X's. They're what go in, the outputs are the Y's. They're what come back out. So what's the next smallest input? Yeah, so let's put 0 into our mapping diagram like this. After 0 and after 3. Very good. Now, interestingly, you're going to see some repetition here. And when I ask you what's the smallest output, what would you say? Let me circle all of the outputs for you in red. These are the products of the mappings, okay? So there's an output, an output, an output, and an output. What is the smallest output that you see? Now, I want you to notice that -1 occurs twice. You do not need to write it twice. In fact, the mapping diagram would be garbage if you did, because the purpose of the mapping is to see convergence and divergence of arrows, which you'll never get to see if you write something more than once. So the fact that -1 occurs twice is like, okay, but we're only going to write it once. It's going to wind up saving us time. Who's the second smallest output? And who's the largest output? Now, there is an empty space at the bottom of that box, and it turns out, since I'm a little more prepared for this lesson now, that it's actually a very good thing to have that little empty space in the bottom. Notice I have 4 in my inputs and only 3 in my outputs. So that's okay. Here we go. Now, what is a mapping diagram? Here's what it looks like. We're going to start by mapping -2 to 3. And what that means is, remember what I said, -2 goes into a machine and comes out as a 3. So I'm going to take my -2 and I'm going to map it like this to the 3. And it's not done yet. I have to draw an arrow on it. Now that's a complete mapping like that. This is just another representation of the same idea of an XY ordered pair. You put 2 numbers in parentheses with a comma, everyone knows what you mean. From this point on now, when you see a number with an arrow, whoop, mapping to another number, you know it means the same thing. What will my next mapping be? From where to where? I think you skipped one. Yeah, we might as well go in order, right? So let's just knock out these points one by one. At this point, it doesn't matter. So let's do 3 to -1. So I'm going to map from 3 up here to -1 like this. Remember to put arrowheads on there because mapping is directional. We want to show someone that the X's are mapping to become the Y's. Somebody would probably figure it out, quite frankly, if you didn't put the arrows. But you still should put them. Who's the third mapping? I agree. I'm going to map from 0 to 4. So I'm going to go from 0 down here to 4. And then there is one more mapping. What is it? 5. Good. So I'm going to map from 5 all the way up to -1, and it's going to look like this. So far, so good. That is what a proper mapping diagram should look like. They can get more complex than that, only in the sense that you might have more arrows to have to draw or more arrows to consider, but that's what a mapping diagram looks like. So that's 2 down, 1 to go. So far, we've talked about this. You can see a relation just as a listing of X's and Y's. You can see a relation as a mapping diagram. Like in this case, if I gave you that mapping diagram, you should be able to tell me what is going on. Like, what are the ordered pairs? The third one is actually just a graph. And so for this, I'm going to bust out my little graph picture here, which is pretty cool, right? I just want to keep those on the screen, but this is the only other way really that you're ever going to see a relation. You're going to see it as set of points, a mapping diagram, or a literally graphed set of points like this. So let's get to it. To graph a point, remember there's nothing fancy about this. This is not slope. Could someone tell me how to get to the point -2, 3? How do you get there? Good job. So left 2, up 3 is going to look like this. Boink. So you put a point right on -2, 3. I know this is hard to take notes. Anything involving graphing is really hard. I get that. You just kind of got to do your best. How do I get to the second point in the relation? His name is 3, -1. How do I get there? Perfect. So blink, 2 down. Nothing exciting, right? How do I get to the third point? His name is 0, 4. Just go up 4. Doink. And what's the last point? 5, -1. How do I get there? Right 5. Perfect. So I'm going to go right 1, 2, 3, 4, 5, down 1, and put a dot. This is boring as all get out. The purpose of these last 7 or 8 minutes has been just to show you these are the 3 different representations of a relation that you can expect to see. Whether it's in my class, on my test, on the YTOP, on the ACT, it doesn't matter. These are the 3 ways we want you to be able to look at a relation. Points, like XY numbers, mapping diagram if possible, and a set of plotted points like this. Okay. Now, what we're going to do right now is we're going to mess this up here in a second. So I don't ask you to do this a lot, but in a moment, we're going to go back and actually mook around with these notes. Right now, I want to talk to you about another definition, and this will be only the second, like this, the last one I asked you to do. We need to define a word now. And this becomes everything. Now, this is our everything for the next few weeks of our school year together is what is a function? A function is a relation. Ready for this? Where each x only maps to one y. And you could, if you wanted to make this more official, you could say like where each input only maps to one output. Here's what I mean by this. Right now, if we go back and look at the relation as it is, as it's written up there at the top of the television, do you see any input that maps to more than one output? I don't. You agree? Like -2 is one of my inputs, right? He's one of my x's. He maps to what number? 3, right? Does he ever later down the line map to anything else? Okay, then let's move on down the line to 3. 3 is my next input. He's right here. Does 3 ever map to anything other than -1? How about 0? 0 is predictable. He says, I map to 4. And then finally, there's 5. And 5 says, I map to -1. So here's what I'm telling you. Everything we've done on the board and in your notes so far, this is a function. Because each input, each x, is only mapping to one y, or output. Now, This is the part where we're going to mess it up on purpose. Ready? I want you to add a point to your relation, and I want it to be this. So this is where it goes off the rails, because now what happens is the predictability of this machine has failed us. Listen, to this point, like if I walked up to the machine, I'm going to circle something in purple here. If I walked up to the machine and I fed the machine a -2 and it went like beep, boop, 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 and it spit me back out a 3, Quentin should be able to walk up to the same machine a minute later, put in a -2 and get out a 3, right? That's that like that predictability, that repetition of results. It should happen that way. But here's the quandary. Take a look at this point and this point. That's where it all breaks down, right? The reliability of it all went to pot, because if I walk up and put in a 3 and I get out a -1, and then Brendan's like, man, that is one dope looking -1. Where'd you get that thing? And I go, oh, go over to the 3 machine. And Brendan walks over to the 3 machine and he puts in his 3. He's expecting to get that dope little -1, right? What does he get? He gets a -4. And that tells us right now that the machine is broken. It is no longer what we call a function. If the same input produces more than one output, it is not a function. Now, let's see what that looks like in a mapping diagram. Obviously, with a set of ordered pairs, what does it look like? It's pretty obvious, but here, I'll underline it for you just in case you're half asleep. See this input of 3? See the same input of 3? Not a function. Let's go down and see how it affects a mapping diagram. So if I go down here to my mapping diagram, considering the red point in the upper right-hand corner of the TV, 3 is still an input, so he can stay, but who do I need to add to my output box over here? Let's add -4. And right now, everything's fine. The mapping diagram as he is fine. But watch what's about to happen. We're about to have to do a new mapping. And that mapping is going to go, wait for it, from 3 to -4. And what you just saw happen is called divergence. And divergence is where like one thing branches off into 2, like a path diverging like that, right? 2 things splitting directions. And so you can see it quite visually right here. I'll circle it for you. When you see this, where you see where I'm moving my pen down here, when you see one number spawning 2 outputs or more, it is not a function. Notice we didn't give a hoot when you had convergence over here. Take a look at where I'm vandalizing right now. You see how 2 arrows converged? That's okay. That's not breaking a function rule. Multiple inputs can converge on the same output, but one input cannot diverge to multiple outputs. And finally, the graph as it is with these 4 green dots is a function. But if we add the new guy, 3, -4, where is he? How do I get there? Perfect, right there. Now you know the 2 that break this. We've already talked about who the bad guy is. The bad guys are the ones up top circled in purple, right? When you see them on a graph, what stands out about them? They're vertical. Very good. So in math, we have this thing called the vertical line test. And here's how it goes. It's like a laser beam. It's straight up and down. And there are videos about this. There are lots of cool animations, and I can find one for you if you'd like. But this is a vertical line, right? And if you grab it, think of it like a stud finder. If you grab it and you're like scanning across your wall, do you see how right here you only hit 1 point? You're still passing the vertical line test. Or right here, I'm only hitting 1 point, right? But as soon as I get to here, the alarm bell sounds, right? The siren, because I'm hitting 2 points at the same time. That is a failure of the vertical line test. And when you see that, you say, it's not a function. So to recap, before I make some sketches, and I'm going to not make any of them look bad, I promise. To recap, how can I, as a student, look at it when it's just a set of ordered pairs like this? How can I tell if it is or is not a function when I look at that? That's the key. I don't care if there's the same y's, but if I see more than one of the same x going to different y's, then I know it's not a function. Okay, how about this one? I'm going to change colors now. How about this green mapping diagram? What's my indicator when I look at a mapping diagram to say you're not a function? What's the divergence, right? If I see multiple arrows spawning from the same place, I don't give a crap where they go. Like there could be 10 arrows going into the same number. That's of no consequence. I'm looking for divergence. If one number has 2 sticking out of him or 3 sticking out of him, then we know it's not a function. And then finally, when we see it in its graphic format like this over here, how do we know it's not a function? When they make a vertical association with each other. If they're right above or below each other, then it's not a function. So I have to be careful now on this part. So I have a little bit more, and then we're going to look at what your homework, it's not really homework, what your next assignment will look like. So stay with me for about 3 or 4 more minutes, okay? For this next part, I am going to sketch some graphs, and I'm going to be paying very close attention to how I do this. So here's an x-axis and a y-axis, and I'm going to sketch a relation. Ready? But you might say, hold on a second. Where did you go? Our first relation had 5 points. How many points are on this purple graph? Nope, bigger. Imagine the biggest number that you think could possibly exist in the universe. Now add the biggest number you possibly think could exist in the universe, and then square that, and then multiply it by infinity. Okay, the point I'm trying to make is this. You could never count the number of points on this graph because it's a continuous curve. Therefore, I could not write it as a set of ordered pairs, and I could not write it as a mapping diagram. However, it is still a relation. It's a big, big, big collection of points, right? All lines and curves have infinitely many points on them. But let me ask you this. Is it a function? Let me bust out my vertical line test, my Scanometer 2023. Are you ready? And when I grab this and I scan it across my graph, will it ever see the purple graph more than once at any given time? So I ask you again, is this a function? Yes, it is. Very good. Got it? Okay, let me undo that. It's my mistake earlier, was not undoing. Let me sketch another graph for you, like this one. And it's hard to believe that graphs like this exist in mathematics, but you've just begun to scratch the surface of what this is. You've seen boring straight lines. There's all sorts of curves and 3-dimensional graphs. It's amazing. But if I gave you a graph like this and said, is this a function? What would you say? Why not? It fails the vertical line test. That is right. If I grab my Scanometer vertical line test master 2023, if I'm right here and I'm scanning, everything's fine, 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 busted. It happens right here. Do you see how the graph, the vertical line tester is seeing points here and here? That's when you fail. So this is not a function. We clear? Okay, just a couple more minutes. I'm going to show you what this looks like on Delta Math, and then I will get out of your way here. So almost there. So in your assignment, you're going to see problems like this. These are the easiest ones, by the way. Ms. Orozco will attest to this. These ones are the ones that are super pleasant. Is this a function? No, it's going to fail the vertical line test miserably. So I would say not a function, submit my answer. And I got to say, Delta Math does this cool little demonstration after you submit these, and it shows you a little vertical line scanner, which is pretty cool. But you see why it's not a function, right? It fails because it exists above and below itself. Let's do another one of those. Is this a function? No. How about, is this a function? It is. And I feel like I get that it looks like it goes straight down, but a curve like this is actually always curving. So if you were to scan a vertical line, no matter how vertical this looks to you, I assure you that this is a function. And you can see like right there, it looks like the graph is on, but it's not. It's constantly curving. Just doesn't look like it. So anyways, that's one section of problems. Here is the other easy one. I see you're starting to pack up. This is the worst time to stop listening because this last one is not easy to understand. This one is easy. This one says, which set of ordered pairs represents a function? Which one would you pick? Like, is the first one a function? Why not? Yeah, it's got a -8 producing a 5, and then a -8 turning around and producing a 9. He fails. Who's the good one? The third one is good. He's got a -8, a -6, a -7, and that's got to be a function. So that's all you're doing in problems like that is just picking the one. Pretty easy, right? This is the one. Pay attention. Sorry, these ones kind of, it's the wording. So first off, is this a function? Come on. Yes, it is. Do you see any one number in set A with 2 arrows splitting out of it? Then it's a function. So here it goes. Watch out. Ready? Watch the drop boxes. The mapping diagram above represents a function. Since, ready? For each number in set A, the input, there is only one mapping to set B, the output.
Why? Just why?
I don't know. But once you get used to it, it's not that bad. Let's go again. Is this a function?
No.
No. So here it goes. The mapping diagram above does not represent a function. Stay with me now. Don't get squirrely now. I need you 35, 82 more seconds, whatever I need. Stay with me. This does not represent a function because, here we go. There is a culprit. There is one number in set A, the input, where there are multiple mappings to set B. So basically, that's how your answers are going to go down. And that's okay. It's a little annoying at first, but it does drive the point home. And I was talking to Mr. Roscoe about this earlier. If you struggle with those, just take your hand and cover up set B. Set B doesn't matter, right? To be a function or not a function really is determined by how is set A behaving, right? So I'm going to go ahead and this is on Delta Math, but for God's sake, you don't have to like get it done today or tonight or anything like that. I'll give you a little more time. So that all makes sense?
Yep.
Ooh, good. I can finish my recording and submit it. Everybody say bye to the recording really loud. Ready, go. That was pathetic. Try again. Do better. Thank you. That was good. One more time. 1, 2, 3.